So Bohmian mechanics, in your view, completes the picture.
Yeah, it's what I call it the rational completion of quantum mechanics. Because, you see, in the end of the day, if I say to a physicist, here is an electron here outside of your laboratory, and it has such and such wave function. I give you the exact wave function, the spin, everything. What does it mean? What does it mean? It means that if I take this electron, bring it into a laboratory and measure and do some so-called measurements with it, then I get such and such result with such and such probabilities. That's what it means. Okay, but if somebody in an astronomer say this planet will be at that place in 6 months, okay, in the sky, it doesn't mean that if I look at it's important about the meaning. It doesn't mean that if I look at the planet with a telescope, then I will see it at such a place in 6 months. That's true also with additional hypotheses, namely that the sky is clear, that my eyes function, the telescope works as advertised, etc. But it doesn't mean that I will see it. It means that the planet will be there. And if you don't know what it means to say the planet will be there, then we don't know English or French or whatever. So that's what the meaning. The problem is that my problem of quantum mechanics, I've written many times that the problem is not the reduction of the wave packet, but it's the meaning. What does the wave function mean outside of laboratories? If it doesn't mean anything outside of laboratories, then you have given up the goal of physics. You may say we are forced to, don't have anything better to do, and that's what more or less what Bohr thought. But it seems to me, first of all, it's a sort of a disaster. Okay, why do physicists celebrate the end of physics as if it was a great, major advance? And it would mean we can't speak about the world. Period. We just speak about what happens in this little operation in the laboratory. But then why do we build laboratories? We go to a government and say I need $1 billion to build a laboratory. And then I say, because I'm going to discover the laws of nature and the ultimate laws of nature, etc. And then in private, you say, no, there are no laws of nature. We're just doing a little experiment to amuse ourselves. But, and then we, but of course, it world goes outside of the philosophy seminar and the government says, what do you mean? You're just amusing yourself. I mean, and then there's an ethical problem there. It seemed to me that, of course, if Bohm didn't exist, if the Boyle Bohm didn't exist, then I don't know what I would think. But it seems to me that it gives the simplest possible completion of quantum mechanics, and in the most vexing sense for the people who have claimed that it's impossible, because it says that matter moves. I mean, as my friend Detlef used to say, I mean, it means that, particles actually move. You see, they have let me close this. So the particle actually move, and for example, in the double slit experiment, the particle goes through one slit, the wave goes through both slits, and because if both slits are open, and then of course that wave influences, guides the motion of the particle in a different way than it would if there was only one slit open. What could be more natural? And you can do that with the delayed choice experiment, you can do with all experiments. You just have a very simple explanation in terms of matter in motion, matter guided by a wave. And the wave function now has a physical meaning outside of laboratory, like the electromagnetic wave. It's weird because it's defined on multidimensional space, but nevertheless, it just, guides the motion of particles. So what could be more simple? I mean, it's just shocking that you say, no, particles actually do have position, and they have position at all times, and their trajectories, therefore have velocity at all times. Totally contrary to the dogma. But if you try to measure the velocity, so-called measure the velocity, then of course you have to set up an experiment, and then you can show that what you are going to measure is not the real velocity, but something which coincides with the prediction of quantum mechanics. To explain it concretely, take a particle in the ground state in a box, then of course that's a wave function which is real, which according to Bohm's guiding equation means that the particle is at rest, so its velocity, we know it, is zero. But if you want to measure it, how do? You can't just look like if you were God and look at the particle somewhere, where the particle is. So you have to remove the walls. of the box. And then by doing that, the particle starts moving, and it moves in certain way, so that if you measure the distance traveled after a certain time and divide by the time that has elapsed, then of course you get a velocity, and that velocity is random depending on the initial position of the particle, and is distributed according to the absolute value square of the Fourier transform of the wave function, of the initial wave function. So it's in agreement with quantum mechanics, and do the calculation. It's in my book. It's not original, and it just follows from Bohm's equation. So that's a very simple example. You can understand why a particle can have a position and a velocity at all times. Yet, when you measure the velocity, you do actually an experiment. You interact with the particle, and then of course you get a certain statistical result. But the point is that every interaction, every so-called measurement, except measurement of position, is an interaction with the particle, and the interaction with this particle is the same thing for spin, the same thing for energy, etc. Whenever you measure and quotation mark measure, in quotation mark, you are not measuring any property of the particle. You are just interacting with the particle, and the result of those interactions is statistically described by the Born-Hole.
Right, and there's no threat to determinism.
Yes, but it's deterministic in a funny way for many reasons. First of all, if it's deterministic, you might think that if you, for example, if you do a measurement of spin in a Stern-Gerlach apparatus, so you take a particle here with a given wave function, given position of the particle, then the particle will have its spin. I mean, the result of the experiment is determined. Of course, the result of the experiment in the end is a position of a particle, because we don't see the spin. You see whether it goes up or down in the direction of the field, of the gradient of the field. But then you can see that in certain idealized experiment, idealized situation, you can have a particle and there can be a symmetric wave function, and then there is another line that the particle cannot cross, and then the particle, if it starts above that line, will go up, and therefore you will say its spin is up. But if you reverse the orientation of the gradient of the field, it will again go up, and therefore you're going to say now it's going to have spin down. Okay. So the problem is that the value of the spin does not pre-exist to the measurement. Again, it's an example where you don't measure, it's contextuality of measurement. You don't measure the some intrinsic property of the particle, even though everything is deterministic. But in order to know what the result will be, you have to tell how you orient your measuring device. So the details of the measuring device matter in order to get the result. So those properties are not real properties of the particle, even though the theory is deterministic. And then, of course, there's something even more interesting, is this hypothesis of quantum equilibrium. If you assume quantum equilibrium, then you cannot go, I'll explain in a minute what that means, but if you assume that, then you cannot predict or control things beyond the usual formalism, so that the uncertainty, so-called uncertainty relation, which are just statistical relation about results of measurement, still hold, etc., etc. You see? So there is nothing, I mean, and quantum equilibrium simply is saying that if you take many, many particles, then their distribution at the beginning of an experiment, if many, many particles all having the same wave function, then at the beginning of an experiment, they will be distributed according to Born's rule, and that propagates with time, so that if you have Born rules at time zero, then of course, when at a later time, at the end of the experiment, you will again get Born's rule. So Born's rule, it's called equivariance, it propagates with time. Then you can say, well, but why do I have them at time zero? Well, you have them at time zero because you prepare it with things which are also origin of the universe. But of course, assuming some sort of equilibrium in the beginning, I mean, also in the beginning of the experiment, or I don't like to speak of the beginning of the universe, but let's say the beginning of your sort of baby toy universe, then you're going to, this is sort of a natural assumption. If you want to explain the increase of entropy, you have to assume that the world started in a non-equilibrium situation, because otherwise entropy would not increase. Equilibrium would be, we wouldn't be here if the room was in equilibrium. There would be a gas or something, and you would be a gas 2 and there will be no communication, nothing. It's only because we are out of equilibrium. We're out of equilibrium is by definition an improbable situation, and then you have to assume that there is even more out of equilibrium.
No, you're right. Bohemian mechanics does seem like the clearest view, and it does seem like the most complete picture that eliminates the most ambiguities.
But I don't know any other. Give me another. I mean, I'm sorry because once you understand it, it's so natural that it's difficult to think of any other because then you just say, oh, gee, after all, quantum mechanics is just mechanics. It's just another mechanics. It's just classical mechanics with different trajectories, but there's nothing metaphysically new. There are no questions that you cannot answer. There's nothing. Well, the thing which is metaphysically new is non-locality, but non-locality could be taken as a defect, but of course, because of Bell, now it's a quality because it shows that it has a property that the world has, not just quantum formalism. So it seemed to me, and then you explain also the measurements, what the measurements are not measurements. So you actually vindicate what Bohr was saying that you don't measure properties, you interact with the system. But of course, he thought it would be true for everything, and then of course there would be no meaning to the wave function outside of laboratory. Now you have given a meaning, but you have not fallen into the trap of assigning values like spin, energy, momentum, etc., to particles, which you know from the no hidden variable theorems of the good ones, those of Bell and Kochen and Specker. That there are theorems that show that if you assume that quantum systems have properties like spin, for example, in every possible direction or something like that, then you can run plus some assumption that I won't go into, which are very natural, then you can derive a contradiction, which is somewhat similar to Bell's proof of non-locality, and you can actually prove non-locality using that. But that shows that Bohm is very natural because it just does not assign these properties which are forbidden by the no hidden variable theorem. So that's a good thing. And then you have the quantum equilibrium that explains why you can't go beyond ordinary quantum mechanics. So in a sense, Bohm, you can say Bohm tells the ordinary physicists, don't worry, everything is fine, just do your work as before, work with the wave function, the operator and everything, just don't bother. But it makes sense. It all makes sense because of Bohm. Okay, if you want to study GR double, spontaneous collapse, then you have to modify quantum mechanics, and you have still problem with the wave function. You have millions of problems, or you have to, if you think in many words, then you have this incredible ontology. There are zillions of copies of both you and me since we started the interview. There are so many strange things, and you're just the mechanics, but and it's ordinary quantum mechanics, but it makes sense, and you don't have entire libraries of mystical books and bad philosophy and God knows what.
Yeah, you pointed out in the book where all the things that need to be taken into account if you take up the other interpretations, like the adjusting parameters on GRW and incoherence and all these metaphysical assumptions that sneak in that don't really need to be accounted for
No. In Bohm, you don't have to do anything. And that's why I find it so natural that it seems to me that, of course, people say, I don't want to be bothered with that, and I use with only quantum mechanics. And you can tell, yes, just do. But if some student comes and say, what does it mean? I don't understand. And what is this blah, blah, blah about consciousness and measurement and so on and so forth. Then you just tell him, well, Bohm when I was a student, Bohr has answered everything, and now you can tell Bohm has answered everything.